Looks like we do. Excellent. Welcome, everybody. And we're already recording, so let me get the screen shared so people don't just have a blank screen to look at in the recording. All right, here we go. So we've got quite a bit of ground to cover because we're a tiny bit behind the other section, partly because we went over in detail a little more than the other one on Dijkstra's algorithm, but also because we had a good presentation about TuTh, which I hope if you weren't here to see in person, you were able to review on the recording or participate in person. So what I got to do here is fire up our projector. And I had a couple of questions people asked. Yes, there's more homeworks coming. I will not give you guys a ton of socket stuff left to do because I had a couple of people kind of say, like, you're killing me a little bit. And it's not a heavy programming class. The department would like to have some programming in every course, so we will have one more of them, but we're not going to have, I'm not going to try to gang up on you and throw like 5 socket labs at you at the end of the semester. So that's just not in the cards. So we have lecture 14 and 15 to get through. 16 and 17 don't exist. So if you're looking on the class folder and wondering where those were, those represented midterm study guide and midterm for the summer for a different one. So I just kept the numbers for the presentation instead of going back and changing everything. So we've talked about the data plane for the network layer before, and this is where the actual switching and the routing gets done. And what we're going to look at more today is what happens at the control plane. So we've looked at the routing protocols, we looked at Dijkstra's algorithm and Bellman-Ford. What we need to look at now is how do we deal with the billions of devices on the internet? Do we have routing tables for every subnet that's out there? Well, no, we really don't. And I couldn't get one of the things to work last time that we were trying to look at. And after class, I figured out it was one of those PIBKEC errors. I don't know if you guys have heard of those before. It stands for problem between keyboard and chair. It means me. So I had screwed up the entry on this. So what I want to do is go back and show you one more time. You know, it was in plain English what I was supposed to type, and I just, was talking at the same time, and it was super tough. So what I wanted to show you is how do you find these AS numbers that we talked about. And Wi-Fi is making me really nervous, and they never gave me Ethernet in this classroom. But this is like crazy slow. All right. University of Houston. Let's see if it'll work this way. Instead of typing uh.edu, which is what I kept trying to do last time. Okay, so here are the 2 AS numbers that we have. One of them is 7276, the other one's 23030. So the whole world thinks of the University of Houston as one spot. Even if we have tons of subnets, and you can see we have quite a few public subnet addresses, then they are all part of the same AS. So instead of other routers tracking each one of these subnets and having to have a routing table entry in every router on Earth that says if you get a packet that starts with 129.7.66/24, send it, this is your next hop, and start sending it towards us. So they're all going to end up presumably in the same place, but you don't want to track these things independently. So we came up with this autonomous system, an administrative domain. If I can draw a circle around all of the routers that run the same routing protocol, that have the same ultimate administrator, that you complain at the same person about, which is like Charles Chambers for the University of Houston, then that's one AS number. Some places have tons more, and one of the things I was really interested in, I have to remember the accent, was the other place that I teach. Here are all of the domains they have. And in fact, I need to add one more thing because it's getting 2 things in here. Okay, so they have 208,000 public IP addresses and 50 different public subnets, and they have 6 different ASs. So that's very unusual. So sometimes you'll run into people that still with ASs, they still have managed to kind of mushroom a little bit, and there's some reasons for that, historical reasons. They were the first place in Latin America with the internet connection, for one thing. and it was TuTh, as a matter of fact. So it was, and I was involved. I remember hearing Farrell Gerbody at Rice talk all about it, and we chatted. It was kind of interesting. So this is a way to look it up. So when it comes time to enter routes in a routing table, you're only on the internet. You're only going to use the AS numbers. You're not going to use actual subnet numbers, and that greatly simplifies your task. So it refers to being able to draw a circle around a bunch of routers with administrative autonomy. So take a company like Xerox. They're a favorite of mine because they have a complicated network. They've got sites all over the planet, regional offices, everything else, but they can be managed as one AS. So you can send everything to one spot and get it into the Xerox cloud, if you will. And then they will take it from there, and they'll have to have routers that know how to convert things to regular routing tables. So there's routing between ASs, inter-AS routing, and there's routing within the organization itself. You do not run the same algorithms and protocols. You run Dijkstra's and Bellman-Ford. You'll find examples of both inside of an organization. And between ASs out on the internet, it's a combination. It's a little different model. So here's a picture of these interconnected ASs. You'll designate a router at the edge of your diagram as being one that is tasked with
just waiting a couple hours
with other ASs. Okay, somebody's unmuted themselves. If you touched anything at all on the mute button when you came in, then you've unmuted yourself, because it was automatically muting you when you came in. So you might want to take a peek. And let me just stop for a second and just help out here. We'll do the. I want to make sure I still did it right. No, I didn't have it set right. My bad. No, I was wrong. I thought I for sure clicked on that. That's crazy. How did it I know I did. It's not my second class of the day. I have a distinct memory. Okay, so there was also a chat message. Let me pull that up here a little bit. Are these UH CIDR ranges for load balancers? Who knows? My guess is no. We probably have more than one subnet range, because we started off small and realized we needed more. And so we went back and asked for more, and the one that was contiguous to ours was already gone. And so they gave us a different one, and then a different one, and a different one, and a different one. So we accumulated them over time. My guess is they are organized logically around different administrative or academic tasks that we perform, like one for Victoria, one for Clear Lake, a bunch for Central Campus, one for out west, one for the medical school that we're building, and so forth, right? One for Houston Public Media, the KUHF TV, and that kind of stuff. But I'm guessing, don't really know. You could try trace routing to some of those devices, just picking a router number. Like if you saw the 66.0/24, try pinging 66.1. It's a decent bet it's the router, or 66. Whatever the last IP, next to the last IP address is. The last one would be broadcast. Those are usually the ones that people will give to routers. And if you trace route and it's got a DNS entry, it'll tell you what the name of it is. And the name is a huge hint sometimes. The name will say something like hpm.uh.edu. Okay, there it is, Houston Public Media. That's the one for the TV and the television guys. So trace routing and pinging things, you can learn interesting stuff by just kind of going through some of that stuff. You can also just pull all the DNS entries if you know how to do that for a particular domain. So the job of these routers that sit at the edge is twofold. They have to speak two routing protocols, and they also have to agree to take on the task of sharing with everyone else to whom they're connected, all the other ASs to whom they're connected, about what they've learned, but only the ones that they directly connect to. So information kind of propagates its way across the network, and that's how you also relieve these routers of the huge burden of having to keep track of where billions of computers are. You just can't do it. It's too much. The tables are too big. So inside of an AS, it's called an Interior Gateway Protocol, IGP, and the oldest one is RIP. It's easy to learn. You could Google for RIP router simulator and find a place where you can go and play around. Most of the time, there are really good network simulator tools, and I'm trying very hard to figure out how to get my arms around one of them called GNS3, which is a GNU public version of NS3. And NS3 is a tool that lets you, in software, um, create a virtual network device, like a router, for example. And that router is so convincingly a particular manufacturer's make and model that you can even download the manufacturer's software that would normally be installed on that router to run the routing protocol, and instead download it into this virtual router that's built in GNS3, and it will run. And with the blessing of the manufacturers, because this is a great tool for teaching people how to actually reproduce problems or simulate networks, or in an advanced lab-heavy class. This is one reason why I keep telling U of H, you need to make this a 4-hour class and add a formal lab. It's crazy not to have a lab in a network class. We need hands-on. So I've kind of given up for a little bit. I take a whack at them every couple of years and see if we can do it. There's a new chairman coming in the fall, and maybe it's a different priority. The chairman we have now is fantastic, but it's hard. It's not just their decision. But GNS3 is one of these. Another commercial example of this is Cisco has a version of this as well, Packet Tracer and some other things. And when you call up for technical support at one of these large providers, manufacturers like Cisco, they will load software. Let's say it's a super hard problem, and the only way they're going to figure out what to do is by reproducing the problem, catch it in the act, and then get one of their developers to write the code around it. This happens all the time. This is why there's 10,000 versions of router code from each manufacturer out there. So what they'll do is load telemetry software on your network, collect the count and the make and model and the software version and all the detailed configurations of all of the devices around this problem, not just the ones that they've manufactured and sold you, but ones from all the competitors and all the ancillary equipment as well, things that they don't even try to make, different types of firewalls or load balancers or switches or things like that. And they will have a way of emulating every single one of those devices virtually using what I just talked about, and they'll do so in a data center. So you can look at a data center with a whole bunch of Intel servers, and that one is emulating 25 different routers, and this one's live, emulating with live traffic, 100 switches this customer has, and they logically tie them all together, and then they have traffic generators that will simulate the mix and make and size and distribution of packets that they saw on your network as well, and they'll run it to see if they can get it to fail again. And if they do, because it's virtual, they've got instrumentation around it that'll, and they'll grab, like, snapshot what it was doing when it happened. So they do not have to go into a lab and build a duplicate of your network, which is good because it's impossible now. And we used to spend hundreds of millions of dollars a year on these labs. It was a huge investment, and have an army of people. There are still a few, and they still have a decent budget to buy some things that cannot be reproduced, or we don't know how to reproduce them in servers yet, like 10 gigabit per second connections. You can't run it quite fast enough for those. Everything else you can. So for those, you're actually going to have a physical server or a physical switch or a router for that kind of stuff. But it's totally transformed the way people design these. So if you're a router software developer, you don't ever have to touch a box. You can do it completely in this Intel-based environment. So this is the way everything gets developed now. Nobody waits until a box comes out. It's all done in these simulators. I had a customer that needed to deal with an old piece of software they had that ran on a Unisys mainframe. This was a competitor to IBM, and they don't make it, I don't think, anymore. I don't think they've gone completely away. There's still a market for some of that, but it was a financial package, and this is a company up in Omaha, Nebraska, and they had a couple of choices when they needed to get rid of this box because it was not supported anymore. They could either recompile the source code to run on Intel, but they didn't have the source code anymore. Very, very common problem. And the person who wrote it retired and then had the nerve to die because they were would have been 110 by now. So they don't have that knowledge from that person. They could have a business consultant like Ernst & Young come in and analyze what problem the software is solving, and then start from scratch, writing a new program in a new environment. It would be super nice. It would be designed with all the new common programming principles that we've learned in the last 40 years, and that would work, but it would cost $1 million. Or just find a virtual machine, like one that you can run on from VMware on a server, and buy a simulator, an emulator for this Unisys machine. So just like I talked about, having a simulator that can emulate a Cisco router or a Juniper switch or an Arista device or something like that, you also probably have heard that people develop iPhone software on an Intel-based machine and everything else. Well, guess what? You can buy a Unisys mainframe emulator. So your software, which has been compiled and therefore is spitting out assembly language, machine language commands, gets received by this interpreter, and it converts it to a relevant Intel assembly language command on the fly. So it's a little slower maybe, but the chips are so much faster now when this Unisys was that it actually runs better than it ever did on the mainframe. So you'll find in networking, this is done all the time, particularly in problem resolution, because the big difference with networking is the whole thing is a live patient. So you're like experimenting on Frankenstein. It's not like if you try to go and reproduce it on a network, you will impact everyone on the network. Whereas if it's a server, you can groom the traffic off to another server. They're a dime a dozen. They're all alike, and you can reboot the server and try all kinds of things. You cannot do that on your network. You do not have a bunch of spare routers at every point along the way, sitting there. So we will use a lot more emulation. So intra-AS routing gets modeled all the time with these tools, and that's one of the other reasons why you have these network simulators. OSPF and IGRP are a couple of other commercial ones. And I always screw this up and say OSPF was the one that Cisco gave away. I probably told you guys that as well. It's like, a bad habit that will not die. It's IGRP that they had. And for a long time, it was a real competitive weapon. If you wanted to run IGRP, which is a really popular good routing protocol, you could only get it if you bought the router from them. So they were using this and that's flipped. The industry's flipped on that now. So now they want you to kind of get the software subscription, and at some point, people suspect that you'll be able to run it on other people's hardware, and they'll still support you if you do that. OSPF is a popular example. Stands for Open Shortest Path First. That kind of makes sense, right? They finally named something with an algorithm that you can understand. It uses link state, but the difference with OSPF is it insists on kind of knowing everything in the AS. It's a comprehensive protocol. It will flood your network when things first come up to try to learn about every single device that's out there. That's not possible on the internet, and sometimes it's really hard to do even inside of an organization, because some organizations are so big that that's too much traffic to have that done. Xerox, again, example. There's no reason why Xerox Europe needs to know all of the routers and build a table for every one of them in the United States when all of the traffic between Xerox Europe and Xerox US all enters the US network at one point. Why not just remember that one? Why bother remembering everything behind it? So sometimes OSPF needs to be segmented and managed in a way where you only learn. But these things all these days have what you would hope for, which is secure channels to exchange routes, so people don't spoof you by injecting intentionally wrong routes and try to trick you into routing your traffic through something else. It will allow multiple paths for something, whereas only one in RIP. You remember one of the key failings we talked about with destination-based forwarding is you only have one way to get to something. This introduces some options for you on that. And it can be, like I said, hierarchical for very large domains. So here's a diagram of what it might look like if you had to segment and divide up your network. This is all one AS, but it's been subdivided with the routing protocol that you've chosen to run in this AS, in this particular case, OSPF. You've been able to segment it into what OSPF determines or calls areas. So there's 3 areas on this. And so you've got some structure in there, and that's a huge help to network managers as well. It kind of keeps things a little bit smaller and keeps you from going crazy with this. But it's just a 2-level hierarchy. And these borders at the edges of these areas take on different responsibility of kind of summarizing, okay, here, let me net it out for you. I actually have everything that starts with this network thing. So I can tell you this instead of the 50 individual subnets because they're all, all contiguous, for example. So you'll have some specialized roles in there. Between ASs, once you leave this world, you're outside of the AS. That diagram I showed you was one AS, for example. Now you are in the domain of the world's de facto standard Border Gateway Protocol, BGP it's called. So BGP is the routing protocol, therefore it is a program that is running on the Intel Unix-based server that is part of every single router that is generating a table of routes that people inside your network, inside your AS, need to be able to interpret in order to make sense of it so they know where I can go on the internet. That's kind of the whole reason you built this thing, is so you can get out of your own network and out to the internet. So the way that happens is from what BGP learns about what the other ASs are that are reachable from you. So this gives you a way of exchanging traffic with other ASs. So you've got some responsibility to exchange things with other border gateways, and you also have to interpret it so that something like OSPF can make heads or tails of it. If you hand a BGP routing table to OSPF, it's like, what's this? You're mentioning these AS number things. I have no idea what an AS is. I was expecting you to give me subnets with subnet masks and next hop IP addresses and port numbers. What is this that you're giving me? So there's some translation that has to happen, but that's the responsibility of these routers at the edge. So the routers at the edge of your network that connect to the outside world actually have a tall order. They have a big task to try to get things done. So here in the dark red lines, the dotted lines, you can see the external BGP communication that goes on, and then inside there's a different type of communication internally that will help people learn what's going on. So the way this basically works is with a path vector. So it's a linked list. It gets bigger one by one element for every hop you have to make. So there's a new network in the bottom right corner of this diagram, X, and AS3 has just discovered that it knows how to reach it. So there's been some communication between here, apparently, and it has, therefore, the responsibility of advertising that to everybody it directly connects to. So in this case, AS3 has a connection to AS2. And it tells AS2, I know how to reach X via AS3. Okay, well, that's him, so of course it's going to be that. But when it gets over to AS2, he in turn has responsibility to tell AS1. He will just tack his number onto the front of this. And so the path will grow by one more. It'll say, I know how to get to X via AS2, and then AS3, and then X. And as a routing protocol manager, when you're trying to calculate the cost to get to these sites with BGP, you just count the number of ASs. You count the length of this linked list. You count the size of the vector, the number of ASs that you have to go through. And you may have to go through a ton of routers in between, but you ignore all of that, and you count it as a single hop per AS. So it's a good thing that routing protocols don't have to give you the perfect route, and it's good enough for them to give you a good route, because that's all they're ever going to do with a scheme like that. So you've got a path that lists all the ASs that you have to go through, and then a next hop which tells you the specific one that you've got to go to next. Policy-based routing is mentioned here, and this is a huge issue on the internet, because the implication from this diagram that we looked at was that if I'm AS2 and I'm, the Schenectady file in Tweezer-Brow Corporation of Schenectady, New York, I may, according to this diagram, let all traffic from the buggy whip manufacturer in AS3 get to the washer manufacturer in China by passing the traffic through me. I don't know about you guys, but I don't really know that I want to give the person who lives behind me in my backyard a shortcut in the afternoon when their street is kind of under construction to park in front of my house and then walk through my house and my yard to get to their house. I'm not sure I'm really okay with that. And in Texas, you're likely to get shot if you do something like that, right? So policy-based routing basically says, just because I could theoretically pass traffic, I can see both sides and I know you're coming from here and you're trying to get there, I don't want to do that for you. So it's called transiting traffic, and most networks will not transit traffic for you for free. So this is why most of the time the connections that we have in reality to other ASs are to large backbone ISP providers, because that is what they do. That's their reason for existing. If you hand AT&T traffic that ultimately needs to get to Sprint's network or Verizon's network or France Telecom or Telmex or Sejatel or Telecom South Africa or any of the other big ISPs, they will take care of getting it there for you. They will not charge you extra to do it. And if they figure out there's a sizable amount of that traffic every day, they will get a hold of that other party and figure out where's a good place for us to exchange traffic. Because what neither one of them want to do is run expensive links. So I can give you a specific example, because this is one that used to drive me insane. In Los Angeles, Equinix has a huge center downtown in Los Angeles. It's an interesting story because this building went for just a ridiculous amount of money in an area where the buildings around it sold for 1/100th of the price. I'm like, what in the world? What is it? The brick? Is there gold? No, it's because of what happened in that building. This is a place where everybody on earth that wants to get stuff into and out of the west coast of the United States has rented a rack. They've extended their network into this building by buying a circuit that extends from wherever they are. This is like a branch office for them. And from this rack and from the router that they put there, they now can, for the cost of a fiber, which is nothing, run connections to 1,000 other networks, 1,000 other companies perhaps. So if you have a lot of traffic that you need to exchange with someone else, you want to be in one of these network exchange centers. And INXs, SuperNAPs, network access points, they have a variety of acronyms. So lots of providers are in here, and lots of big companies are as well. And so this is a place where, yeah, you're going to have to pay for an expensive circuit to get from wherever you are. Maybe it's even across the ocean. But once you're here, it's basically zero to get to whichever collection of these other people you want to, and nothing if you don't. You pay rent, and there's no way you're ever going to leave. This is how you exchange traffic. These are where packets get from your network to another network. That's where the exchange point is. This is like an intersection on the internet where there's 1,000 highways that meet at once. And what used to drive me crazy is AT&T had their own version of this internally, miles away, and they just refused to put a point of presence in here. So every one of my customers that wanted to get to this, what you normally expect is, if you are, say, one big provider, one of the things you'll do is you'll rubber band your network. So you'll have a couple of things, maybe a circuit on the way, but you'll put something inside this network, and therefore your customers have a way of getting from your network over to that one for essentially free. So if they connect and buy a connection from you here, one of the places they can get to on your network is into this address. And then from there, they can get to these other guys. Nope, wouldn't do it. So if you want to get there, you can get onto our network, but then you're going to have to buy a circuit. Well, so what we did was, plow fiber and have a huge capacity, and we just charge every single person a bunch of money to run their traffics to this address. And I'm like, you're just, what's the word, milking as much as you can from these guys? It's not the right thing to do. All right, so that was a big policy decision. But the classic version of this is if you have a couple of people, a couple of provider networks that run across the U.S., and they meet in a couple of points along the way, like Denver and Washington, D.C., and there's a customer who has traffic up here, and they are a subscriber to this network. They have an internet connection from them. They get a monthly ISP bill. And then there's another destination customer down here. They chose their internet service from another provider. So the big question is, are you going to route it this way, or are you going to route it this way? The blue network doesn't like this one. You carry it across your backbone as far as you can, and then give it to me here, because I do not want to carry your traffic. You could carry it yourself most of the way there, and then give it to me at the end. And the red guy, basically wants to hand them first. So the way you'll control this is by deciding whether to advertise these routes to everybody or not. You can make decisions about, I don't want to tell this person I know how to get to this destination, and that will prevent him from sending me traffic, and he will end up carrying it the rest of the way. Most of the time, what we try to encourage people to do is what's called hot potato routing. which is basically as soon as you see a hop that will get it off of your network to someone else's, you hand it to someone else, right? So that's kind of the idea. Okay, so that's a money, politics, and religion layer protocol. That's the politics and money one, right? So that can be brutal at times. There are some providers, if you don't want to pay, there's no one provider like AT&T that really gets to every internet location center on Earth. So there are specialized providers, and this is all they do is provide transit. They don't sell end users internet connections. They don't come out and install routers. They won't build firewalls for you. They don't send a salesperson out. All they do is this exchange. So if you get to where they are, like into one of these internet exchange centers, you can hand them traffic, and they'll get it to thousands of other places on Earth. And they charge you by the traffic you send. It's not a free subscription per month, all you can eat. And one of the big ones out there that's King Kong is Hurricane Electric. And probably never heard of them unless I blabbed about it in this class earlier this semester. But they handle transit. So they've given you one place to go. They don't own all these networks. They didn't build all these networks. But what they've done is gone out and negotiated contracts with all these networks. And so any of these terrestrial or undersea networks that are out there on Earth, they can get you to them. And plus they have a really cool map. So these are all the places they can get to. No one can compete with this. Maybe level 3 can, but here's who runs this data center. So if you are doing a business deal and you find that you need a connection for one of your customers and they're opening an office in a place that you've never heard of before, and you need to be able to pick up their traffic, and they say, look, if I buy my local internet connection from NIS Internet Services in Tirunelveli, forgive me for butchering that name, I'm sure, can you take it from there? Well, look at HE's map and you can tell them, yes, I can. Because this provider has a point of presence in this network exchange center, and so do I. So we can exchange traffic already with each other. So if you get it on their network, if that's who you buy your internet service from, it'll pull all the way back to your main office thanks to me. And I'll charge you by the amount of traffic that you send. So this is a common way of solving the problem of not having a reach. This helps a small provider look really, really big, and it makes very easy the problem. And if it gets big enough, if you're spending enough with these guys, then maybe you'll extend your own network into this location. But if it's like a 1-year contract and it's an oil field services company, which we used to run into all the time, I'm only going to have people there until the well's developed. And once we got the hole drilled and it's producing oil, we're going to camp it, and then all the people leave, except the guys there just to maintain the equipment. And they don't need an internet connection, right, unless there's a problem. So they'd actually set up a branch office, fly trailers in, do all this, build like an office setting there with geologists and everything else, just long enough to get it drilled and producing, and then they'd leave. So Schlumberger would show up. You could pay Schlumberger to do this for you. They'll show up and run all that stuff, but they need an internet connection because the geologists they want to talk to aren't going to move to Siberia for 6 months to do this. So you got to have them on video conference all the time and with cameras and all of that stuff, right? So there's no reason, it doesn't make sense for you to build a permanent network presence in that area for something that's only going to be there for a while. So, there's some sophistication now in the way we tackle these problems, and some really elegant ways of going about tackling it. Okay, so there's some different types of BGP messages. We don't need to understand really what those are. Here we show we've added another connection that's probably going to win the day because it doesn't require going through AS2. And so I might pick that one instead because it's 1 hop and this one was 2 hops before I could get to X. Just count the number of ASs that you have to go through. It's just simple as that. Then in this case, router 1C has the responsibility of pushing that information out to everybody inside the network. How do you coexist with a traditional routing table that's got like normal costs? Like we looked at last time with Dijkstra's algorithm, you have a number, you figure out like, is it 5 plus 3 the best one, or is it 2 plus 6 the best one, or what's my best way of getting there? So this is a problem that you've got to solve when you connect your network. You're going to advertise the paths, and then you're going to have to fix one. And what I'm trying to get to is this diagram here, because it shows some costs that OSPF assign to these links. These are OSPF link weights. And so when TuTh learns that there is a way to get to this network called X, one choice he has is to go this route for 263, but this route is also there. It's 264. It's one higher. But he's going to figure out which one of those he wants to take, because OSPF will run Dijkstra's algorithm and figure out how to do it. But then he gets an advertisement from the other side. And this other side has 2 hops. That's what 2A learns. But OSPF says this is a 201 cost. So OSPF might choose to go this way because it's a smaller number than this one, even though once it gets on the internet, it's 2 hops instead of 1. So you got to decide, which one are you trying to minimize? Are you trying to minimize the cost inside your own network to get to the closest gateway? Or are you going to suck it up and take whatever cost it is to get to the gateway that has the lowest cost from there? So you have to make decisions when you configure these routing systems on how are you going to interpret this data, how are you going to resolve that, which one's going to win, which is your priority, fewer ASs to hop through or lower internal cost via like OSPF to get there. So, you've got some administrative authority to decide how you want to do that. With hot potato routing, for example, you pick the one that has the least intra-domain cost. So you're going to pick the one to the left. You're going to pick 2A, even though it has more AS hops, for example, because you got rid of it sooner, right? Okay, here's the diagram that goes along with what I talked about with policy decisions. Both B and C can get to A and therefore can reach W. But B may not wish to advertise to C that he knows how to do that, or else C will send the traffic through B to get to W instead of sending the link. This link he has may be congested, and if he just lets his routing algorithm run, it may decide among all the places that A knows how to get to, the better way to get to W is to go this way. And so it may build a route that says go through B. And B's like, hey, so it may decide, I don't want to advertise that. Don't give me that crappy traffic. That's your own, that's your own responsibility. So C does not ever learn about the CBAW path. Right? Makes sense? This is a dual-homed network. It has connections to 2 different ISPs. This is a singly home network. For reasons that I could never quite understand, it always made me a little bit uncomfortable. One of the organizational psychologists, whose wife is very likely actually to win a Nobel Prize, who's at Rice, Phil, my neighbor behind me, worked at AT&T and did some amazing organizational psychology stuff. Had some great, amazing stories. If we get bored someday, remind me about Phil, and I'll tell you some really funny stuff. It's excruciating to listen to because he loved torturing engineers, basically. And so he was really good at doing it. And he would tell these stories and just laugh about how painful they were just agonized, squirming, like, oh, no, let us stop. And he goes, no, let's watch the customer struggle with this. And like, no, push the red cable in. So he was funny. He was a funny guy. But when his wife got this job, and he ended up getting hired as well, he switched. He didn't use AT&T for his network anymore. And that always bothered me. He didn't use the very product that he had helped dramatically improve. So he had Time Warner for Wi-Fi. And so we had this agreement where, if my AT&T service goes down, give me your Wi-Fi password. And, so we had this conversation like that way you're close enough that I can just like borrow yours and you can borrow mine. So we were both dual homed, but in a very interesting kind of way. So if you open up your Wi-Fi at home and you see some really strong signals that do not start with the same long string that your provider gave you, it probably means they're using a different internet provider. They could have just changed the name if they bothered to do it. And it's time for you to have an open house party. And instead of asking people, their name and their phone number, just ask them, who's your internet provider? And make friends with a couple of them and teach each of your devices the other person's Wi-Fi password, or help them get a guest network set up. And that way, if yours goes down, you can be dual homed and keep on running. There's my free tip for you on how to actually build a better network for free. Free. Okay, sorry. Apologies to the Rockets announcer. He likes to say three, and do the echo thing. Okay, so that's a little bit on BGP. So why do we have these different routing protocols? Well, between networks, you're more worried about efficiency. With inside of a network, you may be more concerned about policy. Inside of a network, you're willing to build a table with access or with visibility to all the routers. On the internet, it's pointless. It's impossible, so why try? Learn just what you need to make it possible for your customers. So the nice thing is, if you use these NAPs, you actually can hand this stuff off, because it's still profound to decide, how do I learn about all the ASs I need to get to? But going to one of these Internet Exchange Centers gives you the ability to say, you know, all I need to go through is an AS, and then I'm at one of these things, and then they tell me it's like one hop from them. And they can get to like most of the world's networks from there, and all I need to do is get it to them. So that makes my routing tables like super simple. Wherever you're trying to go, hand it to your provider. You can have any color of Model T you want as long as it's black. Right? You just have the single answer for everything. Okay, so that's slide deck 14. And one of the reasons why we're behind a little bit is I have more energy in the morning than I do in the evening. And I tell you guys, you know, more fun stories in this section than I do the one before. So it's self-inflicted totally. But, you know, why not make it more interesting? You know, why should it be not fun to do this? Okay, so a little bit more on the control plane. With SDNs, one of the things that we've discovered we can do, if you teach a routing protocol how to stop looking at just the destination IP address and start looking at some other things, you can teach it rules that make it walk like and talk like other kinds of network devices, like firewalls and load balancers and network address translation algorithms, just from that one change. So we genericize this a little bit, and instead of thinking about them as routing protocols and routers, we are going to go back to kind of a more generic term of switches, and we're going to call these like flow tables instead of routing tables. So the traditional way of doing it, if you'll recall, was to run the protocol, run this program on every single router. This is why there's Unix and an Intel chip. And then the result of every routing protocol on Earth has to be a list of rules, a routing table. And you hand that down to the switch. And the speed is so urgent at this point that in high-speed routers, you actually install the routing table in every card so that it's in firmware or, you know, reprogrammable where, and can run at hardware speed, basically. You do not have the routing card come up and ask the software layer, the Unix program, here's the destination address, where should I go? You have zero time to do this. So you try to install all the knowledge you can in the traffic cop, you send them out to the intersection, and then they're on their own from there. They do not have time to get on the radio and stop every car and ask, and then call back and say, you know, like calling up Metro and go, what route, what's the bus routes I should take to get to here? You just have no time. The cars are coming too fast, right? So it's a profound issue. So speed is of the essence, but only once you've built the table. So what we're going to do with SDN is take all the responsibility away of building the table away from the router and put it in the cloud instead. And we're hoping that we'll have a few breakthroughs when that happens. Number one is we pry that proprietary algorithm away from the hardware manufacturer, who was the only source for it in the past. You had to buy the hardware from them, you had to buy the software from them, et cetera. It's like buying a mainframe 50 years ago. If that's not an innovation that you see immediately, how about one where you can afford, since you have a lot more compute power at your fingertips in a data center than you do in any given server and a router, why don't you take a much broader view, much bigger cast network, and run Dijkstra's algorithm on a much larger number of nodes, let BGP look at lots more of the internet, and calculate better routing tables. You know, get closer to the best route and not just a good route. Make it incrementally better. So that's kind of the idea of what we do here. We're going to centralize the control plane, and with SDN, you know, you have these benefits, right? Distributed programming is more difficult if you push this out into every router. You will still need some software left behind on these routers to actually get the routing table. It still has to have a routing table, so you're going to have some sort of communication mechanism, but it can be relatively rudimentary. It can be a little FTP sort of server, or it can be a little web server, something like that. Just enough to kind of get things done. Like you guys, if you've done much programming with protocols where there's APIs that look like URLs, like REST protocols and things like that, there's ways of doing it. So what we've done is the industry has kind of settled down on a most popular candidate for this that we'll see in a second, to define, okay, if you have a routing table and you want to give it to one of these devices, how exactly are you going to do it? You're going to put it in a packet. How big is the packet? How many rows can it have? Are you going to have encryption? How do you tell it which encryption protocol you're using? So that's been developed, and it's available freely. And you can choose, if you want, to teach your router how to speak that language. So you write some code for your router, and you will now be able to exchange information, including things like, this link went down, I just discovered this new network, here's my statistics for the hour, here's how full my buffers are, all the things that you want a set of protocols to understand, or a set of programs to understand about what's going on in the router. You now need a way to ship that up to the data center, because there's nobody locally that cares. A lot of this stuff's been done anyway, because network managers, they want to know a lot of that stuff already about their routers. Like, how are your statistics? I want to know too, not just the protocol that's running. So the evolution that we talk about is to the mainframe. When I came into the industry, I had a summer job at NASA, and they had tons of mainframes to do the space missions. They were early on in the space shuttle development at the time, and bunch of mainframes from IBM. There were an army of people from IBM. They had a huge office down there near NASA. And you bought the idea was you bought the mainframe from them. You bought the operating system from them. It only ran on theirs. It was custom. It was nothing you ever heard of. CICS, MBS. God, I used to use all of them. And then you had to program in the programming language that they gave you, which was weird, like JCL and some other kind of weird kind of stuff. And you went to their schools to learn how to do it. And if you needed help, you hired one of their people to come. And then you ran programs on these things. And if they were programs that were commercially available that you didn't custom write yourself, you bought them from them. So the whole thing, if you had printers, they made them. They sold you the cables. They sold you the ports. They installed them. They charge you for maintenance. Every detail, the terminals, the networks, 100% of it, sole source from IBM. This is why they got really, really big. And they were super expensive, but the crap worked. And the joke is that we used in the phone industry, if you kick their anthill, more ants come out of theirs than anyone else's. So if there is a problem, they will swarm you with people that will get the problem fixed. No one fails with IBM, ever. No exceptions, right? So if you're JP Morgan Chase and you absolutely need to know your system's going to stay up and you will print out the bank statements and you will make these trades, that's the safest bet. And a CEO is like, I don't care if it costs twice as much. I'm not dealing with people that can't support me like these guys can. And so that was very valuable to the industry, and it made them very successful. They focused on exactly what made the difference. And it wasn't just the hardware. People didn't care what the speed of the CPU was. Right? So that's busted up now. You would never buy a laptop that way now. You buy it from whomever you want. You have somewhat of a choice of who makes the chips. You get the OS you want. The programs come from wherever. You can write them yourself. You can pick the programming language, etc. Phones that way with the App Store to a certain degree. More on Android than on Apple. But that's the idea of where we think we want to get with routing, where you can go to the App Store for routers and download someone else's implementation of Dijkstra's algorithm, for example. So with traffic engineering, it's also difficult, as we've seen. A destination-based routing algorithm will just pick one route and send all traffic over that one route to the exclusion of all else. So if I have, I'll never send things two different ways. That's one problem. Nor will I take traffic that's trying to reach the same destination and at some intermediate point along the way decide to send at a different place depending on where it came from. I don't care where it came from. I don't know where it came from. All I look at is the destination address. That's why it's called destination-based forwarding. So it's tough with the routing protocols we've had but it's easy to implement compared to, it's a lot harder to implement the other stuff. Well, it's time for that to change. So we pull all this stuff up into the cloud. We have OpenFlow, which is the name of the dominant package that will allow you to exchange messages and keep in contact. It's a much simpler, lower level, more rudimentary, not so much lower level, more rudimentary package that you install. Needs a much lighter processor, doesn't need a full Unix kind of server there, so it should drop the cost significantly of these routing devices and open the market for lots of other people to provide them, because all they have to know how to do now is get it to run the CA and talk to the cloud. As long as it knows how to run OpenFlow, it's got the little control agent, you should be able to control it just like you control anybody else's router. So that's where we're headed. So at the bottom, you've got these switches that are controlled. You have an SDN controller, again, from someone like OpenFlow. And your programs that you used to run inside the router, they're now up in a data center. And they can receive information now from lots and lots of routers at the same time simultaneously. So now, instead of waiting for your routing algorithm to propagate across as neighbors hand things to neighbors, hand things to neighbors, now this guy at the top gets an update from all the routers in just one step. So the cloud is its neighbor, and everyone talks first and foremost to the cloud. So in one step, one iteration, the cloud sees it all and can make calculations and converge on a network map and on routing tables much more quickly. It still has to build custom routing tables for every router, but you can do that. Right? It can get done. There are very complex schemes in the middle for how we're going to implement this middle area. You can see simple network management protocol versus OpenFlow. There's some choices you have in the middle here on who's going to handle the table that has all the link state info that you're learning, like this link went up, this link went down, this port just was turned on, etc. You may make decisions about where that needs to be passed. So the idea is you've got somebody at the top that's sort of monitoring things. It can make queries, but it can also receive alert messages. And you now completely change your abstraction of how this works. And if I tell you, I've handed you this data from all these routers, I want you to tell me what you're going to do to build a routing table. You're going to kind of start from scratch as a software developer. You may take a completely innovative approach from the way the industry's done it before. And that's exactly what we want to see. So we want to see you got to do this in open software, if you will. So there's messages that flow from now what we're going to just call switches, but they're really still kind of what we had called routers. But we're not going to call them routers because they're not running the routing protocol anymore. They just have a forwarding table and they're switching. So there's messages between there that's been made kind of flat. And here's an example that shows sending messages from one of these devices through OpenFlow, which is the communication protocol. It has an update for your link state table. A link has gone up, a link has gone down. In this case, this link has failed. The red link has gone down. So I'm going to send that up through my network graphing system because it needs to build a new picture of what the network looks like. That network graph has chosen an app to calculate with Dijkstra's link state algorithm a new routing table for me. It produces the results, and then I hand it out to these three routers, a custom one for each one. So what the response is for this link going down gets handled by software that is now modularized, maybe written by different people, and outside of the router. The only job of the router is to send information up when things change and take information back on what it's supposed to be doing. So this other slide just kind of walks you through what it looks like. There are other models out there. Open Daylight is one that's a different model, same kind of idea. Something that watches the topology, keeps track of the stats, hands things up to these other devices at the top. This one uses a REST API, which if you've done programming with APIs, you'll run into that. If you haven't, you will. But it's a way of using what looks like a URL to pass a whole bunch of variables and their values to another system to get a response back from them. Okay, and then there's ones that the telecom industry uses internally, network operating systems, they call these things. So that concept's been around for a long time. So there's some big issues here. What happens if the data center becomes unavailable? What happens if the link that you had to that one goes down? Well, some people will argue, well, if the link that you have to that one goes down, you don't have any way to get there, how are you going to get to anywhere else anyway? What difference does it make? I mean, if your link goes down that leaves your office, then you're not getting anywhere. So what good would a routing update do for you if the network got dug up? So there's that kind of argument, but people are still very cautious. Should I leave some capability behind in the router so that it can kind of, if it loses connection with the mothership, it can still do some exploration on its own, like the Mars lander? You know, how much autonomy should I teach the thing? And that's going to push the cost back up closer to where it was before. So if the reason you're doing this is to kind of offset cost, there's things fighting against you. Also, are you really going to buy a cheap third-party switch from somebody you've not heard of? Who are you going to call when it goes down? If it's from Cisco and you call them, they'll have an army. Kick the ant pile, more ants come out. That kind of model again. So we think this will be a transition over time, but it's a solid idea, and it's taken root completely in some companies, but gradually in others. So it's got to be a little more ultra reliable. There's a set of protocols that we use to help us know what is going on with routers today. And the dominant one is one that was developed at the time TCP/IP was developed, called the Internet Control Message Protocol, or ICMP. And ICMP sits to the side of IP in layer 3. It's written as part of the code for your network layer, and it can receive messages from devices on the network that send alerts. It also can generate and transmit messages asking for people to respond with information on, you know, whatever type of question you've got. So there are two categories of messages. There are proactive alert messages, and then there are query response messages. And the way ICMP works is devices on a network, the routers and the hosts, all have to be able to respond to and generate these kinds of messages. So although it sits in layer 3, it's not a peer of IP, because it still uses IP to send its messages out onto the network. So they don't have the graph here in this particular. I see a chat message there. I'll get to it here in a second. They don't have the drawing here, but basically, how about we switch back to something that won't, you know, ruin our appetites. So you usually see the network layer drawn like this, with IP in the middle, and this is layer 3, and you'll see ARP down here in the corner, and we'll see that a little more that later. And now we're going to see something like ICMP here. You'll find routing protocols up here. And the way to interpret this placement is as follows. If it's in the top half of the diagram, then it will use IP to send its data and to get answers back. You will see this in Wireshark inside of an IP datagram on the network. If it's in the bottom part of layer 3, yeah, it's still part of this layer. It was still installed with your latest update to your network code, but it sends things out directly to Ethernet just like IP can. So ARP sits down below, and we'll see some examples of these things as we move along. They didn't give us a diagram here, but I wanted to show you, like, how is it possible it's at layer 3, but it still uses IP. So it uses IP like TCP and UDP would, but it's not a transport layer protocol. Okay, so ICMP's got a bunch of code numbers and messages, and they have a format in common that they use. And one of the things you can do with this is traceroute and ICMP. Have I talked to you guys in detail about traceroute before? Have I given it to you in nitty-gritty detail? Have we done traceroutes and I've shown you what they look like and counted? Did I show it to you in Wireshark? Not sure? Okay, so I don't think I have. I usually have mentioned everything at some point by this point in the class, because chapter 1 kind of did a soup to nuts overview of the entire thing, and I usually kind of put a little bit of everything in there. But traceroute is a application layer program. So why is it mentioned here right when I just said this is layer 3? Because traceroute is a program that you and I can run as normal users. It's available to you and me to type at a command prompt in Windows, on a Mac, in Unix, whatever your system is, and it will reach down and ask ICMP to generate a particular type of query response type of message. And I need to give you this in detail. So the purpose of traceroute is to try to discover what's going on between you and a destination on a network. And if you will recall from when we talked about the IP header in a little more detail, one of the fields in the IP header keeps track of how many hops you have left. And so if you send a packet out on the network, you give it a time to live, like 64 hops. And every router that touches this packet along the way will reduce that TTL by 1 and overwrite what's there in that field. And it therefore is going to have to recalculate the checksum for the header as well. And if it ever gets to 0, the interpretation is it's gone too far, it's had too many hops, there's probably a loop. There's probably a circle that I'm going over here. And no router can probably detect it, so this is your safeguard to keep from routing a packet forever. So if it ever gets to a time to live of 0, you drop it, and the router knows to send a complaint back to the source. And it does so via an ICMP error message. So the way traceroute works is normally I have no idea what routers are between me and a destination. So I'm going to send a packet. Any old packet will do. I'm going to send a packet to the destination. Traceroute happens to use always the same type of UDP packet, which a lot of routers have figured out, and then they stopped answering these things, so which is why you see asterisks, and I'll show you what I mean. But basically, you're going to just send any kind of packet to a particular destination, and you're going to intentionally set the time to live to a very small number. You're going to start by setting it to 1. So it's going to get out the door to the first router and fall flat on its face, because the router is going to subtract 1 from the time to live. It's going to see that it's 0 and say, don't know what the number was in the beginning, don't know how many hops this has been on, but I can tell you this, it ain't going any further than here. It's done. You're done for the day. So I'm going to chop off the head of the packet so I have information on which one it was, and I'm going to send a complaint back to the person who originated this packet. Bingo. I just caused them to out themselves. They just sent me a packet directly from the router. I now know the router's IP address. I can look up its domain name. I can figure out how many milliseconds it took to get a packet there and back again. I can learn about this router. So I get that back, great. Then I'm going to set the time to live to 1 higher. I'm going to set it to 2. When it gets to the first router, the router subtracts 1, it still has time to live. That is no different than every other forwarding of a packet it does all day long for billions of packets a day. It's just forwarding a packet, looks it up in the forwarding table, gets the next hop, the IP address, the port number, sends it. Right? Nothing unusual. Every packet has a time to live. Every single packet it does this, subtracts 1. The one I sent it before just happened to turn 0 when it got there. This time it's not going to turn 0 at this one, it's going to become 0 at the next one. And then the next one, and the next one. And so every time I send these packets out, I'm going to keep incrementing the TTL by 1 until the thing that responds was the destination I was originally trying to reach. Maybe it's a website at Microsoft. And now what have I learned? I've learned how many hops I had to go through to get to Microsoft and what the IP address of every one of those routers is along the way. And very often I'll learn who they are. So let's do one. So what I'm going to do is do a trace route to rice.edu. And let's see if it'll get it back. First of all, it's interesting. They use Amazon AWS to host their website. And it's at least 4 hops away. I'm seeing some struggles here because whatever the 5th hop is ignoring me. They see my request, and they know that it's not one that they care to answer. Maybe they don't want to be dragged down. Maybe they think it's a denial of service vector, and so they've taught their router, don't ever respond to these. Or maybe they just don't want me to know who they are. And then so I give up and I send one with a TTL of 6. The next guy does the same thing to me. I send one with a TTL of 7. He responds. 8, 9, 10, 11, 12, 13 respond. Doesn't. 14 and 15 do. And eventually, God help me at some point, I hope, after 16, really? How many hops does it take to get to Rice's website? I can see them from the top of this building. I mean, how far away is this thing? So what's happening in the meantime, I'm going to stop this. Well, maybe I'll let this one run a little longer. What I'm going to do, I don't want that. I'm going to create another window. Okay, that was okay to do like that. I'm going to start Wireshark. And I'm going to show you what this looks like. So I'm going to stop it. Got to 18 hops, and that was as far as I got. All right, my machine's being super pokey here, so I don't know if we'll finish this. Oh, come on. How many times do I have to click on the wrong window? Methinks I have too much stuff running. All right. Really? Does anybody hum Jeopardy music for me? Thank you. Thank you. Let's give it a little boost here. Let's start. It's this ghetto Mac I'm using for Armageddon that I bought off of eBay. I have like 6 of them or 5 of them or something crazy because they don't make them anymore. So I feel like one of these hermits, you know, like on some movie where I survived an attack. Okay, let's go open Wi-Fi, and what I'm going to do is start filtering for ICMP packets. And I'm going to run this again. And all I'm going to see are the error messages coming back. And you can see as it builds up on the left, some of these don't respond with anything, but the ones that do respond with an ICMP error message. So we'll let 5, I think 5 and 6, right? Wasn't that the drill? Neither one of those things responded. So we'll let it run a little more. And then we should get through 7 up to 13, I think. Come on, give it up. Okay, thanks. All right, good. And now what I'm going to do is stop my capture, and we're going to go to one of these things up at the very beginning. So this says time to live exceeded. This is the error message back. I send 3 packets to each router so I can average the response time. So I have 3 complaints, and they all come from the same source here. In fact, I got, looks like 2 only, not 3. The third one got lost. Is that right? Yeah, third time did not respond with a response. So it got too busy. The next router, here's his IP address. Here's the next one's IP address. The next one's IP address. So where are the ones that I sent out? So if I get rid of my filter, and you can run this at home, absolutely, positively. So here's the time to live exceeded message. What I want to look for is who was I really trying to reach? The ICMP error message should tell me I was originally trying to reach 52.0. So here is the error message right here in blue. Here's one of the messages to 52.0, and here's the other. And remember, it only responded 2 out of the 3 times. The third one's up here somewhere, but I'm going to forget about it right now. So here's the packet that I sent to Rice, to their IP address. If I look inside the IP datagram, I gave it a time to live of 1. Do you see that? A time to live of 1. So, of course, it's going to generate this time to leave error message. And then I sent another one, also with the time to live of 1, and I got an error message back. And then I sent a third one with the time to live of 1, and I never got anything back from it. It timed out. In the meantime, I sent a boatload of WebEx packets. And if I continue on, you know, down here eventually, I'll see, you know, more of these things with the time to live of 2, etc. So what I can actually do, if I go back up here and find it again, I can set a filter in Wireshark by saying conversation filter for everything with this pair of IP addresses. And all I'm going to see now are the things back and forth between me and Rice. Okay, so here's a message to Rice, a time to leave exceeded. Here's another one that went to Rice, but I got error messages back from the next router. Why? Because the one I sent here had a time to live of 2. And down here, I had one that had a time to live of 3, and so forth. All right, so I'll give you a little bit to practice on that later. So traceroute, again, is a request that's made from the application layer program called traceroute down to ICMP to ask it to intentionally generate a packet and set its TTL to a small number. Ping is another one. Ping is another program I use. This one asks a site simply to respond with its reachability. it does so by asking ICMP to build and send a particular error message. So there's a bunch of other junk in here that we don't really have to go through. And then this last section in here talks about network management, but we've talked about that. We talked about it enough. I'm not going to give you questions on it, so in the interest of catching us back up to where we need to be, we're just going to kind of do an exit stage left on this one and forward a little bit past it. Not surprising, it has a protocol, there's a data structure, it's 4 bytes wide, we fill in the spaces. Wow, right? So if you are interested in it, there's a good 10-minute discussion in yesterday evening's lecture. But I don't want to have us fall so far behind that we can't get to anything else. We can't stay behind. That's what I'm basically trying to say. So I got 2 minutes left, and I'm going to use them. So the next layer down is the link layer. This is where Ethernet lives. And one of the things that there's some profound differences in here. It's not just like the next layer down. It's got a lot of things that make you think it's just another layer down. It's got addresses. Every device has its own address. It's got protocols. They're 4 bytes wide. It takes things from above and it sends them down below. But the big difference here is this is the first point at which what you're really interested in doing is getting two things to talk to each other over a wire or over some other communication medium, point to point, not going through anything else, through nothing, directly. This is the nitty-gritty. This is your last step at the bottom of the stack, basically, before it turns into bits. So if it's Wi-Fi, then what I'm concerned with is getting this antenna radio to talk to that radio, but not to talk to one that's 3 hops away on the other side of a router. No, 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 no. Only on the local LAN. So this layer deals with building LANs. And on a LAN, if you can't see the device, if it's not on your LAN, it's completely unreachable to you. So if I'm trying to send a packet to the other end of the world, I'm going to do so by traversing lots and lots of local area networks to get there. And I'm going to do it by traversing nothing but local area networks to get there. And so between a host and a router is a LAN. Between this router and the next router is a LAN with a subnet, with its own addresses, with its own layer 2 protocol for error detection and collision, etc. So that's the kind of fundamental concept that we've kind of got to get across. So this is the actual segment layer, you know, getting on the train, getting in the car, getting in the bus, sort of one hop at a time. If you have to get out of the car and get on the airplane, that's a different LAN. That's kind of the idea. So what you're looking at when you look at the wire are streams of bits, and they all look like bits. You can't tell by looking, look right there, there goes the beginning of a frame. It's quick, grab it. No, it looks like every other 1 or 0. So one of the things that, and I'll leave you with this, one of the things you'll have to do is reserve some patterns of 1s and 0s for every one of these layer 2 technologies that are prohibited from being used for data and instead are used to have special significance to control and delineate the information. So for example, with Ethernet, if you have 7 bytes of 1s and 0s alternating and 1 byte where the last 2 bits are both 1s, that can never appear in data because that pattern is how you tell that the beginning of an Ethernet frame is coming up. So you see those 8 bytes and that's how you know, here comes ready, 1, 1. Now, that's your first bit of your Ethernet frame. And that's when Wireshark starts grabbing, and that's what shows up in Wireshark that shows you here's how big my Ethernet frame is. It knew to do that because the card is always watching for 1010101010101010 and so forth. All right, so that's a pattern that's reserved. Every layer 2 technology has to have those, and there's lots of other rules that keep the communication going. But we'll have to pick this up next time when we get back together on Thursday. So I'll see you guys then. Thank you very much. We went fast, huh? A lot of stuff. We're getting there. We're getting there. And let me look at the chat. There was a question I didn't answer. How would disaster recovery be implemented in SDN? So what we used to do for customers that had franchises is a hint to that. Like Blockbuster, we deployed a network to Blockbuster, and there were, at the time, 8,000 stores. No, wait, 7,000 stores. Hold up. Now there's 6,000. Wait, hold on. 5,000, counting down. And we would run an inexpensive ADSL high-speed line or cable modem line to them. But the devices for that industry, the routers that people buy, also have slots like PCMCIA slots, but they're not those kinds of slots. They're different kinds of slots. But you can buy other communications technologies with them, like cellular cards. So Sprint sells cards that you can pop into one of these ports on a router, and it's emergency backup in case your line goes down. At least you can log into the router and see what the hell's going on and figure out, is it the router that's down? Is it the network that's down? Do you need to just try to reboot it, etc.? So you can do things like that. Just use a completely different layer 2 technology, wireless typically, right? And there's a company in, of all places, Tulsa, Oklahoma, that was like King Kong at doing this stuff. They could go out and implement, it's an unbelievably complex project to flip a customer from one type of infrastructure to another. It's a zoo for a year and a half. It's just unbelievable. Consumes them. So good question. All right. See you guys later. Bye, everybody.